to all my dear colleagues. I haven't seen you, I don't know, for the last 5 minutes at least. So I'm going to talk about the paper on third generation district heating compared to fourth generation district heating that we are doing as a follow-up to this project we had on fourth generation district heating. And actually it has two parts. First, there's a part on an agenda, so I might as well take it from there. First, I will just introduce a little bit about what is this fourth generation district heating anyway. Then we have made some literature studies. We both made a qualitative and quantitative literature study. We've been counting how many papers and so on have addressed fourth generation district heating, and we've also pulled out some of the results from some of these, and I've put some very few bullet points on. I've just been compiling this based on a 20-page paper. So lastly, there's a comparison between third generation district heating and fourth generation district heating based on some energy plan simulations. And I should also put the footnote to your attention that this is not something that I've been doing. It's an idea that Henrik and I would develop, and then we involved a lot of people to do the work. So we have Miguel, who's been sitting there compiling all the information that everybody has been sending his direction and structuring, and he also did a very large literature review, or rather he did the quantitative literature review where he was analyzing where is it mentioned in what context and how has that developed over the years. Peter, who's been in charge of the energy plan analysis, Fred, and let's see, and Ole from University of Southern Denmark, working at the framework conventions. Jan Erik from Danfoss, who's been working on some of the charts, describing the evolution from the first generation district heating to fourth generation district heating. Sven Svendsen from the DTU, who's been doing a lot of work on buildings and also assessing the cost of switching buildings from third generation district heating to fourth generation district heating. Another Sven, this one from Helmstedt, who is our basic data guy. Whenever we are uncertain about what should we set the efficiency of this unit for in 2045, then we invite Sven, and then he says, how about 95%? 95% it is. Carsten from the Department of Energy Technology and Grids. So we've involved a lot of people, and I've probably forgotten some which I've now offended. But just to start with fourth generation district heating, this is from a concept paper that was published a few years ago, describing how the efficiency is increasing over time, and how temperature levels are decreasing over time. The first generation system is based on steam, and we still have some of these systems here and there, and even in Copenhagen, there's still some steam-based ones. Moving towards pressurized, so that's water in excess of 100 degrees, and then towards third generation, which is what we have today, which is non-pressurized, so its temperature is usually 80, 90 degrees, and then towards fourth generation district heating, where we're still debating about what should the actual level be. But in our concept paper, it's 50, 60 degrees, but people are already introducing new generations and even lower temperature levels. One thing that was not mentioned so much in the initial concept paper are district heating return temperatures. When you're condensing the steam, you're getting hot water, 80 degrees, 70 degrees, 45 degrees, and for these systems, you may get all the way down to the lower 20s. So that, of course, means that you cannot heat up a room with a small radiator like this one, because it simply does not have sufficient surface area to supply anything. If you feed it with 40-degree hot water, it will not heat up this room here. So we need to rethink the entire building mass, floor heating, for instance, I mean, if we heat up this room with floor heating, if you put in 45 degrees in the floor here, then that would be uncomfortable. I mean, you wouldn't like to put your feet on the floor if it was so hot. But for a radiator like that, it is too little. So it really depends on what is our building infrastructure. Some of the other differences is also in terms of what are the technologies that you can actually put into the system. And for instance, one of the things that we're also looking into in our comparison between third generation and fourth generation, that is, if we are going towards the lower temperatures, then we have more surplus heat from different sources that we can actually utilize. For instance, if you have a supermarket, they will have some cooling equipment, and then they will be producing some hot water, or maybe some warm water, maybe that's a better word. But in the system here, where you might be running on 80 to 90 degrees, then if you have some hot water at 40 degrees, well, sure, you could raise the temperature with heat pumps and so on. You could introduce an extra electricity demand. But if we're getting down to something like 50 degrees, then you just have to raise the temperature very low, so you can actually use it more efficiently. And for some sources, you can actually also use it directly, so without even boosting the temperature even further. So we have new options, and we're moving towards fourth generation district heating systems. So that was just a little bit about what is this thing called fourth generation district heating anyway. But let's move on to see how it has developed over time. So this is the chart that Miguel made when he analyzed, simply going to scientific databases, looking into who has done work on fourth generation district heating and how has the number of papers developed over time. So going back to 2014, we are, so it's 25, so that must be exactly 18 articles, more or less. Different colors, whether it's distribution grids, whether it's something from smart energy systems, whether it's building systems, whether it's heat sources, or whether it's a planning and implementation, or whether it is something else. So, but they are all about fourth generation district heating. It is all people who are explicitly referring to fourth generation district heating. So this is in the academic literature. So there's been a very large surge in the amount of literature that has been published on fourth generation district heating. I might add, for historical reasons, that when we made the fourth generation district heating project in the beginning, a research consortium in the beginning, it was simply that felt that the district heating sector needed something. Because there's always a lot of focus on electricity, there's focus on transportation, but district heating had been living a simple life. Many systems were established decades ago, and not a lot of things were happening there. But they were feeling that they're being, I wouldn't say out-competed, but there's a competitive edge. I mean, electricity is moving into areas, and you can then establish heat pumps, and there's all this grid power, and so on and so on. So district heating needed some development also. So that's why this entire fourth generation district heating consortium was established. So in academia it has worked, but likewise in parallel also outside in the actual district heating companies, I would say that we've seen a similar development, that people are really eager on changing the district heating systems. There's a lot of work in Danish district heating companies on how much can we lower the temperature and what heat sources can we get from wherever. I mean, of course, you living in Aalborg, you know that we have a lot of district heating from Aalborg Portland, but other places they don't have cement factories, so that they really have to go out and make very detailed mapping of the industries, both like the traditional industry, but also the service industry, trade, etc., to see where can we actually get some heat to use in our heat systems. So a large development in academia, but also in real life applications. Now I will present a little bit on some of the findings from this literature review that we made based on this graph here, or this chart here. It's about buildings, it's about distribution grids, it's about heat sources, it's about smart energy systems, and it's about planning and implementation. And again, I've just taken some few bullet points out of a long article where we tried to make a synthesis of all the work that has been happening on this. So, as for building systems, there are two steps in the transition, and one is easy and one is more difficult. First of all, the first step is we can simply, in today's systems, reduce the return temperature. That is simply on how we're controlling the systems. That is how we're controlling the radiator valves. It's how we have the temperature set points if we have some intelligent systems in our buildings. And that is the first step towards low temperature district heating. Secondly, then we can work on reducing the forward temperature. Once we start reducing the forward temperature, then we have some added benefits from that. We have some losses, which I'll come back to in the district heating grids, which are lowered, but we also have some production positive sides, with that. In as much as the efficiencies of the CHPs and boilers and heat pumps and whatever simply increases. The lower the temperature requirement, the better the production technology. We can reduce the temperatures, as I mentioned before, if we are not stuck with small radiators like this, but we have large radiators, or we have floor heating for that matter. Then we can reduce supply temperature down to 45 degrees. With floor heating, you can go lower than that. They can go down to 30 degrees maybe. But we need some intelligent systems. As it is now, we have many house owners who do not have very much control over the radiators and actually supplying hot water back into the system, and that increases losses, and it means the production system is not very efficient and so on. So we need more intelligence in our house systems. One of the areas which is particularly difficult, that is domestic hot water, because there we need some higher temperatures. I mean, even though I could ask anyone, what is the temperature of the shower? Any guesses? Nobody wants to say anything stupid. If you take a shower, what is the water temperature?
A warm shower.
Yeah, of course a warm shower.
40 degrees.
Yeah.
It cools.
Has anyone ever tried taking a 50-degree shower?
No.
Nope, that is completely impossible. So anything in excess of 40 degrees, that is extremely uncomfortable. So, and I would say even 40, I've tested it, of course, because otherwise you wouldn't be standing against it. So, but that means that for hygiene, personal hygiene, we're talking about 40 degrees, but for cleaning, then it might be 50 degrees. But that means that we have to have something, if we have a heat exchanger, then we need to have something like 55 degrees to be able to provide domestic hot water at 50 degrees, of which we only use that partially. But you'll notice that that number is higher than this, so we'll have to find some other ways of providing domestic hot water. So different options are proposed. I myself have worked on booster heat pumps as a means of doing that. Simpson has worked on electric heating, where you simply put a coil into a hot water tank to increase it from, say, 40 until 45 degrees. One of the main issues that is Legionella, the bacteria causing Legionnaires disease. So that dies at higher temperatures, but if you simply leave water at 40 degrees standing in a tank for too long time, then it will be perfect breeding ground for Legionella. So, on to energy savings. We can save about 50% of the energy demand in Danish houses if we do it primarily together with other renovation. If you have a house that does not really require any renovation, then it's very hard to make a good economy out of doing anything to the house. My own example, I live in an old house from 1910, and I'm sure I could find some energy savings potentials in that house. However, I'm paying 10,000 kroner per year for heat. So even if I half my consumption, and I didn't consider that some of the 10,000 is fixed, and then I could save 5,000. And savings would cost me in excess of 100,000. So energy efficiency should be in houses with renovation. We've made similar analysis, or we have found similar analysis in the Czech Republic, where it's in Romania, indicating similar savings potentials. So this is what is economically feasible as long as you're doing it together with some other renovation measures. For the grids, first of all, we are probably moving from the traditional tree structure where you have a solid branch and then some thinner lines heading up to the different buildings, also known as a radial structure, towards systems with a ring structure, because we are trying to move to a situation where we don't have a point supply, but we have a lot of points supplying into the grid. So we'll not just have the local power plant, we'll have the local power plant and the industries and supermarkets and crematorium and whatever, basically as we have in Aalborg. So double pipe service pipe systems. This is a double pipe system as opposed to a twin pipe system where you have two separate ones. Can reduce losses by 6 to 12%. We can generally, if we're moving to lower temperatures, we can decrease heat losses. We have an example here where we're moving from 28% 4080 down to 19% simply as a consequence of the temperature. Because the temperature is directly, or rather the losses are directly proportional to the temperature difference between the soil and the water you have in the pipes. So if you have a high temperature difference, then your losses will be high. Low, it will be proportionally lower. Heat sources for fourth generation district heating systems. Well, as I already mentioned, we have some sources which are available, and the lower the temperature, the more you have available. In the example I have from Denmark, we've actually put some numbers on it, so there I will come back with a more quantitative data on that, but let's just talk on a more qualitative level here. So all these sources from industry, waste heat, power generation, waste incineration, and also in the future from the production of synthetic fuels for the transportation sector, for instance, they will be perfect sources, and the lower the temperature requirement, the more we can exploit directly. We have also made some analysis of what other sources. We don't have any waste heat sources from industry, etc. Well, seawater, that's an excellent heat source for systems. The only problem, of course, is that the efficiency of the heat pump you need to produce the district heating water will, of course, be lower with the lower temperature you have in the winter than in the summertime. But still, we've made analysis that it still pays, even with the lower COP of the heat pump in the wintertime than in the summertime. Then we have been reviewing the work that has been looking into fourth generation district heating as a part of smart energy systems. Some of the work is, a lot of the work that we're presenting is work that we've done, but we're not really looking into first done it when we're doing the review. So, for instance, for the EU 27, district heating where applicable, individual heat pumps elsewhere, so replacing all individual biomass and gas and whatever boilers, and some strong heat savings. We can get the same fossil and biomass fuel consumption as the EU energy efficiency scenario, but at considerably lower cost. And jumping to China, similar with district heating and a smart energy system for China. we can reduce primary energy supply significantly and also do it at a lower cost. In China, they do have district heating, but they have made a political decision that district heating belongs south of the Yellow River, and not north of the Yellow River. So moving north, we can actually explore a lot of district heating potentials there. We've also made some analysis of Denmark. So again, excess heat from transportation and some energy savings and a little bit of solar thermal will result in lower system costs and a better integration between electricity, heating, and transport sectors. Yet an analysis, one of your colleagues, because that was his master's project from last year, where he analyzed smart energy systems versus traditional energy systems in CEPR, showed that if you have this sector integration, and that includes district heating, then you can integrate a lot more. I think he went from 20% of wind and PV in a stupid renewable energy system, so to speak, to 49% with the same excess electricity in the tube, simply by sector integration and including the heating sector. At the same time, he limited the amount of biomass. It's actually what is sustainable biomass consumption in Zagreb or Croatia. So there are some potentials for the integration with the other parts of the energy system. Planning and implementation of fourth generation district heating. This is one of Frede's bullet points, or one of the bullet points coming from his work. There's very much focus, if we look at it from a European perspective, on the integration between countries, but not so much focus on the integration within countries, between sectors. So the EU, for instance, they have some explicit goals for actually connecting European countries, whereas they don't really care about connecting transportation sector and heating sector and electricity sector inside of Denmark, which of course makes sense because they really don't care about the Danish energy system as such, but they do care about energy markets on a European scale. But of course, that gives an unbalance and imbalance in the policy making, and of course that is something that we should also focus on. Geographical information systems, essential to evaluate the design of district heating and cooling potentials and strategies, mainly due to the very specific nature. I mean, every district heating system is specific to its own place. I mean, we have this very specific layout of the district heating pipes, which is based on, well, for instance, if you have a Limfjord in the middle of the town, then you can have pipes going this way, or you can, but it's more difficult. And it depends on what are the sources, and it depends on a lot of things. So we need some good tools to be analyzed, or to be able to analyze this and to assess district heating and cooling systems. Some of our colleagues have been involved in this Pan-European Thermal Atlas, where they've actually identified places where you have large heating demand, but also identified areas where you have large heating potentials. And that could be existing power plants, which are simply not producing heat, simply wasting the heat to nature. So that was the little literature review that we've been conducting on fourth generation district heating. Then moving on to the more analytical or quantitative analytical point in our article, with comparison between third generation district heating and fourth generation district heating. We simply take a starting point in a scenario, and from that we have then developed a clean, so to speak, third generation district heating and a pure fourth generation district heating system, and then compare them. Same energy demand, same biomass consumption, same excess electricity generation, same gas exchange with surrounding systems, So if we were talking about life cycle assessment, you would say that this is kind of our functional unit, that we're supplying the same demands and we have some of the same input factors. Those of you who have used energy plan, you will know that you can't simply tell energy plan that this is what we want and then ask energy plan to find a solution. So you need to have some recursive analysis in that. So it is a matter of changing wind power capacity, electrolyzer capacity, and I think that's basically that. Peter's nodding, he did it.
Yeah, really.
Yeah. He's nodding because he's sleeping. Yeah, that's the biomass banks. Okay, we didn't write about that in the paper. Yes. Anyway, this is just to run through some of the main assumptions. Temperature, and here it's important to notice that here we have a delta T of 35 degrees, and here we have one of 30 degrees. And what influence does that have? Well, it actually means that our pipes will not carry the same amount of energy. So we have to make sure that the pipes can actually supply the right amount of energy. And that's actually some area for discussion. We might change these numbers so we actually end up with systems which do have exactly the same capacity. Weight losses, this is actually, well, these are the numbers I showed you before, but simply as a matter of finding the difference between the water inside the pipes and the soil, and then both for the return and for the forward pipes. So direct proportionality between that. District heating heat pumps, coefficients of performance. Well, below the temperature, we will of course increase that. So that's nice. So we can even, if we decrease it even further, we can have it even better. But so, look, this is for resource temperature of 35 degrees. So that is if we have some industrial waste heat sources that when we need to raise the temperature a bit. Then that, of course, is also influenced by what the temperature requirements are up here. We have some waste heat sources, and there we found, or it's a little bit difficult because we don't have any perfect good surveys of this on a national scale. We found some analysis. We could triple the amount of waste heat that we produce directly, and then we would also have something from district cooling. And I think actually there's a line missing in my table because we also have an element. No, that's there. So we also have some where we are using some electricity to boost the temperature. So we're talking about, we have to keep track of the temperature levels here. So we have some which is directly usable and some which is usable through heat pumps. Efficiencies in combined heat and power plants. The electric efficiency is not changed, but the thermal efficiency is. Biomass boilers, also higher efficiency. Thermal storage becomes a little bit more expensive. And why is that? Well, that's because we don't have the same temperature difference. So that means for the same volume, we do not have the same amount of energy inside it. So therefore, we really need a bigger storage if we want to have the same, or we have a higher cost per energy content. Similarly with solar thermal, we're not necessarily modeling a different type of solar thermal. It's simply that a solar thermal is more efficient with lower temperatures. And that means that per production it is actually cheaper for the same solar collector to produce fourth generation district heating than third generation district heating. Last slide, so I will make it almost on time. This is a comparison of of the different ones, we have a number of factors which are identical. I'll not focus very much on those. Just to say that we have a smaller district heating demand for fourth generation district heating than third generation district heating, simply because we have the smaller loss in the pipes. We have some elements which are the same in the systems here, but we also have some elements that are different. So for the fourth generation district heating system, we need less wind power to match the energy demands of the system, and we need less electrolyzer capacity to match or to have the system in balance, which also manifests themselves in our costs down here. It is not, well, it's up for debate what word we want to use, whether we want to say marginally or significantly, but it is less. So even if we say that, all right, it is not extremely much less annual cost of running the entire energy system, we do also have some added benefits up here. For instance, we don't need to find so much room for wind turbines, for instance. Biomass, yeah, that's the same. Practically. So with fourth generation district heating, we have some benefits. It's cheaper. We use less wind power. We can use more waste heat sources in the system. We have higher efficiencies in the system. We have lower losses. And that is all what I'm trying to say. So, any questions to that?
Would you like the floor?
Yeah, I have one for the costs. I'm just wondering, do you include like all this building, changing the
Yes.
radiators and all
Yes.
of this?
Yes.
Okay, so yeah, and then you save on investing in wind and so on.
I can't. It's been some from BTU has been looking into those costs. I think he said that some of the, Peter, now I'm looking at you, some of the costs will be incurred anyway, so that was not counted. So this is, so it's not everything that is counted.
But it might be interesting to see in the article the different, like where are all the investments
in the article we will,
because here you kind of hide where the differences are.
Or you can add that the whole idea of the article is to answer that question.
Yeah.
That's first question.
Yeah.
So what we put this is in the order of magnitude of 200.
for the building costs for the radiators and the control systems and in the buildings, it was something like 100 million euros.
That's including the apartment buildings cost. There's an extra cost there because you need to put in some different other items. So the cost for the radiators and stuff like that, that's around 20 to 40 million a year.
Okay.
Yeah.
And then that's like 16 million extra for just installing apartment buildings.
And then we also include the cost of operating the grid. That so far we calculated as additional costs, additional company costs, that would then be much lower than So the last time I saw the difference there, it was like 300, wasn't it? Now it's like 200 million.
Let's see if the numbers aren't fully updated. I mean, this is work in progress. And
Okay, that's fine.
these are the numbers. The last time you saw it, exactly. The last time you saw it, in this one here, I include the building costs.
Okay, I see it. Okay.
Yes.
How do you decide that it was the offshore wind power that should be reduced and not the onshore with PV?
First of all, we don't have room for more onshore. Well, there's more room offshore. For PV, I don't think that was up for debate actually. But we have had some other analysis showing that there are some proper ratios between PV and wind. So for here we simply kept it constant. Yeah, but it's just a matter of also wanting to not complicate. I mean, one thing to realize, this is a kind of small analytical add-on to an article, which is basically reviewing an area. So it's not really the in-depth analysis that you would want to do if the entire paper was about this, because then you would really make more scenarios and take people into different areas. So this is just like to exemplify what can be the consequences. So we do not intend to make the full scale of all the different changes that can be made. So simply to talk, this is a 3D8 system and this is a 4D8 system.
It looks a little bit like there's a larger heat capacity in the CHPs.
Yes.
How come?
Because you can more efficiently produce heat to a lower temperature.
Okay. But the capacity, this is the capacity installed.
Oh, that's
Or not.
because this number here goes back to the efficiencies that I had on a previous slide.
Ah, okay,
So
so you
with
have the same,
So with the same electrical capacity, then you'll simply have a higher heat
that makes
capacity.
sense. And you can't
Because of
reduce the
higher
electric
efficiency.
capacity.
Sorry?
You can't reduce the electric capacity.
Same answer as to earlier. We wanted to keep as much of it constant and then simply move a few things around. We're not opening all the different areas.
Okay.
Yes.
Yeah.
When you talk about this development into a ring structure, I know this is not the core of the analysis, but do you have any take on what the challenges is related to this new ring structure?
First of all, I think you will be, it's not the ring structure, I think it's a challenge. If it is a challenge, I think what is the challenge? That is simply that you're going from a system where you have generally or very often one supplier and then to a system with multiple suppliers. I think that's the issue. So from, I mean, for the electricity system, there you actually have a transmission system operator who's in charge of making sure that everything is in order, and you don't have corresponding to that for the thermal systems. But it does, of course, change how you operate the system if you're going from one point supplier to a multitude of different suppliers. And imagine if everybody with a solar collector, they will also start producing heat into the grid when the sun is shining. So we have a different system that needs to be operated in a different way if we're going into the ring structure, but not so much because of the ring structure. So I think there will be we need more clever management of the system. But that is also something that I know that the district heating companies that they're working on. I mean, setting up accurate models of the hydrogen networks to analyze what are the temperatures, different places in the system. As it is now, then for all the systems, you need a certain temperature to provide domestic hot water and to provide enough heating on the radiators. But up until this point, very often it has been the case that if you had one in the most distant corner of the district heating grid, where the temperature got too low, then you increase the temperature in the entire system to be able to supply that customer with adequate temperatures. And that, of course, is a very inefficient way of managing it. And there are several ways of doing that. I mean, maybe you should have you can even have an electric boiler up there to assist the system if it's not occurring too frequently. Yeah. Or you can have some shunts when you sure that you have some water that comes in the forward and gets returned in the return pipe. But again, shunt pipe is not very nice to operate because then you are increasing the return temperature. So you don't want to do that, but you can do it. So there are some things that you need to do to run the system more efficiently. And I've seen some numbers that you can reduce the grid losses by some percentage points simply by having a more intelligent operation of the district heating pipes, how all the different valves are controlled and so on.
Do we have any tools to kind of model this?
No, you don't.
Okay.
Then you really need someone in thermal energy engineering, because I can't remember what it's called, the tool they're using.
TAMS.
Thermis, yes, there's a tool called Thermis where you can model pipes with pressure losses and temperatures and whatever happens in heat exchangers and how pumps are affecting systems and so on. It really, it's beyond energy planning. So we've actually been discussing whether we should put it into the BIM bachelor, but when we found out how much was required to simply get our students up to the point of understanding what goes on, it was quite a lot.
Okay, I think we have to go
Yeah.
on. Yeah, thank you. Yeah. Thank you.
Who's next? First one is yours. Wonderful.
I just called it something. That's the one with the building. Good morning, afternoon, evening. My name is Susanna. I'm going to talk about district heating too, so it's your lucky day, pretty much. I came in from Copenhagen. I've been a research assistant since 2016, and I started my PhD a while ago. I think I have a slide even, so let's start. Go ahead. There we go. My PhD is based on two main projects. Room of Europe, which is something that we've been doing for the past 2.5 years, and I'm pretty sure my colleagues are very sick of hearing about. And the District Energy and Cities Initiative, which is what I'll talk about today a little bit. And it's a project that we run with UN Environment and Copenhagen Center for Energy Efficiency. And it's about districts. That says district energy, but it's basically district heating and cooling. So it really is your heating and cooling day. This is the basic working question of my PhD, so it's not so related to this paper, but this paper should somehow feed into it. Basically, how can we compare district heating and cooling strategies? Like Paul said, it's all very local because heat and cold and thermal energy in general is quite particular in that you can't bring it over long distances, and it's very inherent to the way that it's being used in buildings. So there's a lot of very local aspects to it in how you design the system and how you set up the system. But from an energy planning perspective, there are a lot of similarities when we go to different countries. Paul kind of alluded to it, but we've been modeling the EU, basically, which is 28 countries, and then 14 countries within the European Union specifically. And we know that there are a lot of similarities, that you will find a certain amount of heat savings somewhere between 30 and 50%. So of course there's a range that is particular, but at the same time, there are commonalities between them. So the trick is to kind of find out what the commonalities are. And part of that is what we're doing with a lot of mapping. Like I said, 14 countries in Europe, and then within the DES initiative, we're doing 4 pilot countries outside of Europe. Specifically China and India, which are kind of like lots of countries together. A Chinese province is kind of similar to a European country when you look at the way the system is set up. Chile and Serbia. So those are the 4 main ones that I'll talk about a little bit today as well when we talk about the mapping of it. To start with, what is the DES initiative? Basically, it's a collaboration between UN Environment and what used to be DTU Riese, and is now called the Copenhagen Center for Energy Efficiency. And it was set up under the framework of what is called the Sustainable Development Goal 7, which basically aims to give everyone in the world affordable and clean access to energy. So that's a pretty major task. This is one of the 5 accelerators which look towards energy efficiency. So there's access to energy, there's access to electricity, there's access to clean cooking energy. But one of these kind of subsets is energy efficiency, and this is a part of that. So the idea is that we can try to both increase the efficiency of systems which already exist, but also bring efficiency to heating and cooling in general. In a lot of places, heating and cooling is even less thought about and planned about than it is in Europe. It's a bit of a different context because in Denmark, heat planning is a really integral part of energy planning. In the rest of Europe, heat planning is not a very integral part of energy planning. It's kind of more gas planning. But in places where heating and cooling, firstly, may or may not really happen, and secondly, happens a lot with biomass, which is basically kind of found and not necessarily traded in the formal market, there's no planning whatsoever. So this is the ambition overall, to try and address that a little bit and bring some planning and efficiency to it. The way we do it is in 4 steps. We start with what we call a rapid assessment, which is basically try and figure out what exists and what could be done. We have a team of 2.5 people, so that's kind of the scope that you're looking at. This isn't like a consultancy with 50 people trying to figure it out over a year's time. But from a technical level, we try to find out where the heat demands are, where the heat demands aren't, what the kind of potential excess heat sources are. And we try to link that with where there is kind of political intent and political support. Because without the political support, it's not really possible to build anything. So it's basically a quick scan of what happens and what could be possible and where it's worth investing further resources in. We then move to a deep assessment, which is basically normally finding consultants who can do that work for us and do a much more detailed analysis of what could be done and what kind of projects are available. That usually involves doing what we call a pre-feasibility study of a pilot project. So that can be something like replacing a boiler, replacing pipe systems. In Serbia, a lot of it is how we move towards 4th generation district heating or 3rd generation district heating in some cases. But also, I mean, where could you start putting down some pipes? What neighborhoods would be a good option to start a district energy system with? Then it moves to more feasibility studies and procurement plans. So we'll talk about it a little bit later on, but one of the challenges is that to do a real feasibility study, which a funder is interested in investing in, it has to have some specific requirements. The main requirement being that you are insured for that, because otherwise you're never going to be able to get funding to be able to do it. So that's more helping along with the process and having a technical objective towards guiding that into the right way. In theory, after the procurement preparation, funding comes and the project gets built. That doesn't always happen, but that's the overarching idea behind it. And then we take what we've learned in these first 3 phases and we move to a master planning phase with the local authority. And that basically involves gathering up the challenges that we've come into and trying to make a more overarching plan. Because up until then, the focus is very much on let's try and build something, let's try and build something. And then the final phase is trying to make kind of a 20 or a 30-year plan for how you can expand that and how you can then start working with that and what your next steps can be and how you can start integrating the district heating and cooling with the other sectors of the energy system. So that's the basic overview of the steps that we take. We have 3 formal kind of objectives in it. Part of it is this application of tools. There's a lot of different tools out there, and there's really nothing wrong with that, but it is a good idea to have an idea of which tools are better for what and why they should be used for particular purposes. Capacity building processes. Capacity building is basically a fancy way of saying that we don't want to be doing this for the rest of our lives. So we would like to teach other people to be able to do it for themselves. Like I said, we have 2.5 people in Copenhagen and then we have 5 people in Paris. So, you know, that doesn't really spark the revolution. But if we can go through these steps and then allow for other people to be able to replicate them, then maybe we can expand a little bit and we can do more than just the 8 of us can. And then, particularly in this master planning phase, there's this idea that we should be looking at enabling framework conditions. And that fits in with this idea that we can plan a lot of things technically and we can make these, really nice systems, but if they're not implemented and if the conditions don't exist for them to be implemented and for them to then be replicated, then there's not much point because they won't kind of come into existence. I'm sure it would be nice to make a little diagram about how we can fit that into the 40H objectives overall. But yeah, so that's a bit of the background of the general overarching what we're trying to do here. The reason that we started this kind of review work and methodology development is primarily because we started running into some challenges. The idea of this rapid assessment mapping turned out to be really time intensive. Initially, they were meant to be planned for about 3 months, and one of them has been going on for 18 months. So something's not really working out there. And the problem with time consuming is that it also becomes really expensive. And that's never good for anyone. And, that's basically more time we spend on that, we can't spend on other things. So there's an opportunity cost. The second thing is that, as you can see in the later phases, we start working a lot more with local consultants, and that's fantastic because neither does everyone have the technical capacity to do all of that together, but also they typically have a lot more kind of local knowledge. And when you're working in such different countries, that makes a lot of sense. But they do have different practices, they have different tools, they have different ways of approaching things. And again, that's not a problem, but it does make sense to have a look at why those things are different and what the purposes of those different things are. And also if we can kind of parachute some best practices from some places to others, or if it makes sense to replicate some things, if it makes sense to avoid some things in the future. So those kind of different approaches in a lot of different places mean that it's worth looking at why that's happening and what the details of that are. And the third main challenge, to be honest, is that the data in different places is always different and always special. I think you and Miguel are going to talk about Chile next week.
Yeah.
Yeah. So, yeah, the data can be completely different. In Belgrade, we have pretty good data, except for the fact that it's 15 years old. So, it's measured, but maybe not so current anymore. In Chile, we don't really have very much data other than the amount of wood that people use, but there's no real specifics on what type of wood that is, how humid that wood is, how much energy is actually in that wood. We just know that it's something cubic meters. And in China, it depends a bit, and in India, there's a very good knowledge of how much electricity is being used, but then there's no real understanding of how efficiently that electricity is being used. So we still don't really know the cooling or the heating demand. So basically, this kind of methodology review is to organize this a little bit and see if we can put some structure into it. That's the main objective. So I'll focus a little bit on mapping because that's where we've gotten the furthest, although it's still very much work in progress compared to what we're putting out. And the first part of the review is just looking at what's being done. We made a catalog of best practices in terms of a lot of European mapping. So going outside the scope of this project, just looking what kind of mapping had been done and why that had been done, what the purpose of it was. And that's the first kind of issue, that everyone loves to do mapping because we all know that heat and cold is local, but it happens for a lot of different reasons. In our cases, a lot of the mapping happens to identify potential projects and identify future projects. And that works with looking at, where the high heat demands are, where the high levels of excess heat are, and seeing if you can kind of bind those together in some way. When we start doing that more formally and we start looking more specifically, then basically we're mapping to find infrastructure costs. We're mapping to find out how much pipeline you need, how large the pipeline needs to be, and how much it would cost to dig it in there. Which is similar in a way because you're still trying to look at the locality of heating and cooling, but it has to be much more specific and you have to have a much higher level of data in order to do that in some accurate way. As I said, ascertaining viability, that's quite specific to when we come to feasibility studies, and that really has to be within a certain range of certainty and with a set level of sensitivity analysis so that we can basically take to a bank and convince them to fund us. But a lot of mapping also happens kind of in a broader way. When the heat roadmap Europe mapping is done in PETA and what we'll be doing in heat roadmap Chile, it's also about looking at what are good neighborhoods to start with and what could you be doing in the future. One of the things we do is we look at existing power plants and then we look at how old those power plants are. Because if that power plant is expected to be there for the next 30 years, it's worth doing something with it. If that power plant is going to be gone within the next 10 years, then probably it's not really worth doing something with it. But that kind of mapping is much more long-term than should we build this boiler house or should we build this pipeline? So there's a wide range in the purposes that mapping is done within district heating and district cooling alone. And that's not always evident, that it's not always kind of explicitly stated when we do this kind of mapping. So that's the first thing that we found. The second thing that we found is that data is variable, and we knew that. But we tried to categorize it a little bit. In places where district heating already exists, and it's more about renovating the district heating and trying to implement new sources and make it more efficient. In some ways, there is more data because at least someone is producing the heat. That may or may not mean that someone is actually measuring how much heat is being used, because in some cases that doesn't really happen. That also doesn't really necessarily mean that anyone knows what the buildings look like or how good the buildings are. But at least there's a semblance of kind of structure about what's happening. Like I said, in some cases there is just really no data. Like it's kind of working on a whim and seeing if we can find some key examples that we can then extrapolate to other places or something like that. When it comes to measuring data is hard, firstly because you typically have to do it over a winter, and that takes 12 months, and that's expensive. But also because you have to choose really carefully what you decide to measure. Like there's no way that you could even in a city like Aalborg go and measure every single building. So you have to pick your typologies of what you're measuring, and then you can extrapolate that to other places. And that's very sensitive because if you happen to pick a building where someone enjoys, wearing shorts throughout the whole winter and heats their house to 25 degrees instead of 18 degrees, then suddenly you have a whole skewed vision of what that building type is like. And the last thing is privacy. Privacy goes both ways. Privacy goes towards the consumer. So if we measure something, then we can't necessarily just share that with everyone. But in a lot of cases, the privacy also goes towards companies which hold its data. So if you have a district heating system already, we did some work in Poland where district heating exists and district energy consumption is measured, but the district heating companies hold that data and they don't have to share that because it's their business data basically. So there's an element of availability there as well. Even if the data exists, that doesn't necessarily mean you can get your hands on it. So basically, we looked at all these different kinds, and then we looked at all the different purposes and the drivers behind how it was done. And we kind of tried to make these categories of the types of mapping that we should be doing. The first one is initial mapping, which is basically parallel to this very quick scan that we want to do in these rapid assessments at the beginning. And what we want to do there is we want to take a broad geographical scope. We basically want to look at a city or a region and say, what are the options? And that comes both from supply side and from a demand side. One of the things that Paul said, you talked about in PETA that we're looking at these synergy regions about where there is both high demand and both excess heat. So it doesn't only make sense to look at where the heat demand is, you have to look at the heat supply, which is something that is quite common in Denmark, but doesn't really happen outside of here, to be honest. And we can kind of accept that there's a high level of uncertainty there, by which we can be within like a range of 100%. Like we can pretty much be 100% on or off. But it's more that we can compare areas to each other. And I'll show you some examples of it later. Yeah, and the trick is to do it relatively quickly. What we're moving towards trying to do is, instead of trying to aim for a certain outcome, so to say, we want to know this and this and this and this, we basically make a list of prioritizations, as in this is most important, that is most important. You should have an idea of heat demands, you should have an idea of heat supplies. If that works, you should start trying to develop the synergy regions. Then if that works, you can start looking at what the kind of network options are, but put a time limit on it. So basically say that we accept that we won't get perfect results, but we would like them within a certain amount of time. Then after that, we can start looking at more detail. And again, we can still use a lot of assumptions in that. We can still use these building typologies. We can still look at kind of models of what houses are, or models of what neighborhoods are, rather than trying to measure data. But at least that'll allow us to have some more detail and some more viability on if these projects are viable and if the planning makes sense, than necessarily if we're trying to do it with measured data. Because that's basically the third step, to have measured data and really be able to secure this feasibility. I think I've got a slide on it later on, but basically it's expensive. So it doesn't make sense to do that really detailed mapping and detailed data collection if there isn't a reasonable chance that it will lead to something. And in those first two steps, we can find out if there is a reasonable chance that it will lead to something. The fourth one that we found, which doesn't really fit in any of the other categories, is basically that when we use the maps and when we go to workshops and show them to people, it works really well to visualize something. Just because you have a power plant 5 kilometers away from you, I mean, most urban planners know that they have a power plant around. But somehow, literally putting it in a PowerPoint and being like, this is, 4.7 kilometers, makes a difference and makes it easier for people to understand that this is a potential source of heat rather than just a power plant, which happens to be in your neighborhood. So we don't really know what to do with that one yet. That's why it's in brackets. But it is kind of remarkable that if you tell someone in words, it doesn't really carry the same message as if you put it up on a slide. So these are some of the examples of these 3 categories. Like I said, we did a review of mapping that had been done and mapping that exists outside of our pilot countries and our application countries. This is Amsterdam, and Amsterdam has the advantage that it has extremely measured data because the gas company is semi-nationalized. So the data from the gas consumption, which is the only way that we really heat in the Netherlands, can pretty much be put straight through to the government. This is somehow anonymized in the sense that there's no exact data on this map, but it's put into kind of classifications and categories. But it basically means that you can look at which neighborhoods are the most energy intensive. I don't know if anyone's ever been to Amsterdam, but it's a pretty obvious kind of city layout. This is the center, and then it goes out, and basically further out is newer, further in is that kind of historic stuff that you see in the pretty pictures. And it kind of it allows you to give you an overview of what happens in a neighborhood like this, or in a city like this. Basically, these purpler areas have high heat demands because they're old. As you go further out, it becomes a lot better. North of the harbor was developed later, so that's a lot more energy efficient. But you can see here, this is called Zagos, this is the southeast part, that there's a lot of really high consuming areas, and that's basically just because it was built before the oil crises. So it's your kind of like typical brutalist architecture, which basically leaks heat all over the place. It's not a particularly high income area either, so there's not a lot of kind of cash capital for people to invest into their homes. And it's typically big apartment buildings that are rented out. So if you wanted to do something about different neighborhoods, you could have a pretty quick look at this map and have an idea of what you could and couldn't do and where you should focus your efforts. This is only heat demand mapping, so there's no supply sources on here. But you can put those in and start kind of looking at those regions pretty quickly. So basically, this is an example of something being quick. The database exists, so all you really have to do is put the database onto a map. And it gives you an overview of which neighborhoods are important and which neighborhoods aren't necessarily important. And it's very good data. I mean, it's measured, so that typically gives you an idea that it'll be within an accurate range. This is some work that a colleague of mine did in Temuco, which is in Chile. Chile is really big. The south part of it is pretty cold because you kind of go towards the South Pole almost. They have penguins, so that's kind of cool, but that gives you an indication that there is a significant heat demand. You can see that this is a lot less granular. It's still working with this idea of which neighborhoods are relevant and which neighborhoods are less relevant. Basically, it's based on a kind of survey of a few houses. I think there were 6 houses in total, and those were correlated with income. So this is your basic high income area. This is your middle income area, and then there's a bit of a middle income industry area here. And these are your low income areas. The primary reason being that in Chile, your heat demand is driven by your income, both in terms of the house sizes and just in terms of how much you heat. So based on that, there were these 6 houses where we had kind of pretty good data in the sense that we didn't really know how much energy they were consuming, but we knew what their walls looked like and what their windows looked like and what their roof looked like. So we can make an assumption based on that and kind of extrapolate that and then make these general neighborhood assessments. This is a pretty interesting case because we're working here with both the municipality, which is really interested in doing kind of whole city-wide district energy. But one of the main people that's driving it is NG, which is an energy company, which is interested in having a district heating system. And they're actually most interested in having a district heating system here in the center, primarily because they've done some work there with energy savings, so they have a really good idea about the data. And the heat demand is high, and therefore it makes sense. But the municipality is tugging a bit because the main problem that they're trying to solve is not so much CO2 because they heat with biomass. So it's not so relevant. It's more about the particulates that go into the air. And we've been trying to make a map of where the particulates are released or where most of the emissions are. And it turns out that most of the emissions are in the lower income areas. So that's something that we didn't really realize we had to include, but it makes sense to overlay those layers with each other to see where it has the most impact. So those are the kind of things we learned. Basically, it's not very accurate. Like, this doesn't help you make a system of any type. But it can give you an idea of where you should start and start a dialogue in that. And again, it's because we didn't have very much data. So this is a bit more particular. Here, the objective of it was to identify some potential projects. And particularly, it was a cooling project. And cooling is a bit different from heating in that sense. Because district cooling systems are typically a little bit smaller. And they generally don't really concern residents. They concern companies. They concern office buildings, and that helps a lot. So this was basically just made by sitting down with a series of urban planners and some people who were involved. That which is kind of surrounded by blue are these future development estates, which is where they basically want to build industry and office parks in the future. And those projects are being managed by people. So by sitting down with the urban planners and the project managers and kind of talking to them and being like, well, what exists currently? Okay, this is an IT park. We think it has about this much cooling demand. Okay, this is an office building. it has this many square meters. We think has about this much cooling demand. So in a sense, there was very little data. The data that we had was pretty good. But even that kind of gives you an identification of what exists, what you can do, and where you can start, which is really the kind of objective of it. The result of it is that they proposed 4 projects that could be something and that they should look into, the kind of dark blue surroundings, of which at the moment we're doing feasibility studies of 2 of them. So kind of after having an actual look. Like I said, the advantage of cooling is that usually someone has an electricity bill. So then it's more about finding how that electricity is being used to cool. And then based on that, they found 2 of them where there's viability to kind of continue onwards. But it's a different example of kind of mapping. It's very untraditional because it doesn't involve overlaying maps. It's basically involved a bunch of people pinpricking on a Google Maps version. But it allows you to start looking at where things happen, and actually it gives you a pretty accurate assessment of what is likely to be your potential. This is for Belgrade. As I said, they have some pretty good data in the sense that they've mapped their network, like most district heating companies do. But they don't necessarily really know how much energy is being used, how efficiently. The state of the building stock isn't very known and isn't very good, and has changed a lot over the past few years, but no one's really put any attention and faith into that. But here the ambition was really to be able to identify some pipes that could be renovated or some buildings which could benefit from renovation in order to make the network more efficient. And because there was already an overview of what happened in the world, it was pretty easy to kind of continue with that and move quickly. So we really kind of wanted to be very accurate with this from the beginning. And this is pretty much what you get. I couldn't really get rid of these. But basically we have some building typologies, and those building typologies we validated a few times, so they're becoming better and better. And then based on that, we have energy classes. So the lighter green, the better the building. We've got some over here, which are a lot less green and kind of buying into the red. And then we have the mapping of the network. And then based on that, you can start looking at capacities and what happens if you change certain capacities. If you renovate in other areas, then does that mean you could reuse heat somewhere else? And you know, you can really work with some actual analysis. The last one is a kind of similar aim for it. Like we really wanted to look at a potential network and see what exists and what could be done. And it's the same city in the south of Chile, well, middle south of Chile. It wasn't kind of super granular. We still have assumptions about the buildings. We made some more assumptions about the buildings and we kind of extrapolated. But you can see that we can start building a network. Like we can start linking the different houses with this kind of typical tree structure of a network and start looking at what the size of the different pipes should be. So what does that leave us with, other than a big confused mess of maps? Oh, sorry, just the last one. So mapping for feasibility, like I said, this is very dependent. We can't really develop a general methodology for this. It's basically, what does the bank require? With the kind of caveat that typically if you have to measure data, it's very expensive, it takes a lot of time. And even then, you never really know. I mean, inevitably, you're going to have to correct. If it's a cold winter, then it's cold winter, so you should correct upwards. If it's a warm winter, then you should know that probably your heat demand is going to be a little bit higher. The variation between how people behave and how people kind of act is huge, so you have to somehow account for that. So that's something where we know that there are concerns, but we haven't really dealt with them much. Oh, I put it in the front. I'll go back, sorry. Here we go. So these are basically the three categories that we found. The initial mapping so that we can have a basic idea where we accept a high level of insecurity. This kind of more detailed mapping where we zoom in a bit and we're still working with a lot of assumptions and we're still accepting that we don't know everything, but at least it allows us to know if it's worth continuing doing this kind of work and analysis, and then eventually, mapping to make the system work, hopefully. Those are the three categories that we're working with at the moment and that we're trying to kind of structure and make some lists with. So the open issues that remain, before we can start writing it all up. All of this is very much based on bottom-up modeling. So we go to people, we look at the situation, and then from that we try and build a system. What we're starting now in Chile with the heat roadmap system is basically top-down modeling. We make a system where we look at the whole country and we look at the larger demand, so that which is given for the country, and then we try to distribute that locally. And that's a very different approach. So we're going to see if we can incorporate that in some way into this kind of review and methodology overview. This issue of can we issue some general guidelines? We can, for the purpose, we feel pretty confident that we can issue some general guidelines. Namely, this is what if this is what you are trying to do, then you can use these kind of methodologies and these techniques. But other than that, does it make sense to work with these building typologies like we have in some cases? Does it make more sense to work with measured data that's not so evident? What we're going to find out in the next year, does it help? Does making this overview and putting all these people together actually kind of speed up the process? Is it, like I said, we had this issue where something which was meant to take 3 months ended up taking 18 months. Does it actually help? Does it speed it up? I mean, can it make these systems more efficient, and can it make these kind of analysis more efficient? And then this is specifically for mapping, but can we replicate this kind of review process in other areas too? So those are the things that we're still not sure. If you have inputs, I'm very happy to hear them. And yeah, we have to present this in a non-scientific forum in a few months. And then Lars and I are going to work on putting a paper out of it, hopefully after August and September time. So that's the basic plan for it. Any questions?
I think we'll wait with questions because you're already into Peter's time. So it's like,
Oh, sorry. I was looking at the. That sounds
unless
good.
there's like a short question, but otherwise we will take the questions in the end.
There's just mass confusion. That's how I feel sometimes. But.
Yeah. Because we need to yeah, I think we don't have time for a break because we lose the room 15 minutes past.
It's in the other right corner.
You want a little time for a different course?
Yeah, I thought it was compressed.
Okay, so this is ongoing research we'll talk to you about. So some of it is new and some of it is a bit old. And actually started with Henrik presenting the first time, where we presented some graphs and got some questions. I was like, well, might as well just explain how we got these graphs. And then we can expand a bit on that. So it's mostly me who do the work, Søren, Henrik, and then the guy. And it's quantifying the influence of wind power and photovoltaic on future electricity market prices. Which, of course, I cannot keep the title short. So the start of it is, of course, these mirror order effect, as I assume you've heard about all of you. Everyone is learning. And the missing money, has everyone heard about that also? Yeah, so then, the difference is just whether or not never want to take this. There's a lot of money for wind power and the PV, and the missing money is for the power plants that we might need when the wind is not blowing. So it's related, but not the exact same. So that's the start of it. And what we wanted was a sort of a method for quantifying this, figuring out how big of an issue is it as we go forward, and is it actually an issue? So the method for that is first looking into energy, because we calculate it as an energy. And when we do energy plan calculations, we need to do the market economic simulation strategy. We want to investigate electricity prices. And this formula here is the most important formula when we talk about the market economic calculation. And that is because it calculates the price of the external market, this PX. So this is the most important formula because it decides at what time different units operate, depending on their marginal cost of operation. And to simplify it, this here, that's the distribution file put in for the external electricity market price. So that you set yourself for each hour. And these two here are the two constants that you add in the program. So they're constant for the entire year. Meaning the only value that energy plan actually calculates is this one. And that is simply just the net import in every single hour. Any questions for formula? No. Then we can continue. So normally how we do the market economic simulation strategy, if we want to do one of those. I'm one of the few who actually does it, so I'm not sure really. But we take some historic prices, put them into energy bank, where we have some setup of some existing system, and then afterwards we get a new price actually. We get a price where we affected it. But that is a bit weird if you're doing a reference model. Because we start out with a price where this system actually already affected the price here. And you end up with a price that's been affected twice, you can say. So it's a bit weird and doesn't really give us the right one. So here, this here example is, this is Nord Pool spot in 2015. I put into Independent where I have modeled Denmark. And then I get this price. And these two are not the same. The principle should be if it's the same system. So I think this method would actually give us an issue if we start using that, at least to investigate this missing money, because the electricity prices will be completely skewed. So we can do a bit different. We take the formula from before, find px, and then we try to find the pi instead. Meaning, what would the price be if we did not have the system affecting the price? Meaning, we try to subtract the system we model from the price to get a new price that we can then put into it and see what happens. So the one becomes this instead. And of course, the reason why I want to do this, I want to do a reference model that's actually validated according to the electricity price. Because otherwise, I cannot say what is the missing money issue, what is the mirror problem. So we start the new method that we did before. Take historic prices, put into energy plan. Then instead of just stopping, we instead take this the hourly electricity import and export. So distribution of the B net import. What it calculates. What is this? Then we use the new formula alongside this one to for each hour calculate what would that electricity price have been if we did not have this import export. And of course, this is very sensitive to the factors we have, the two constant factors. And of course, this is a bit simplified because there's a lot of things that affect the electricity price. There's not simply constant through the entire year. But it gives an approximation. That's what we really want. So we go from having electricity price here to getting a new electricity price that looks like this. Where we subtracted this system. Then we take that price and put it back into it. And then the way we then test whether or not this is a good approach is this similar to this? Because that's actually what we want. We want this one to be equal to this. So that is the approach that we should that I suggest. And then of course, the smart one will probably notice this one, but Peter, now we changed the electricity price to put in, so of course this one here will change. Yeah, so you might potentially want to repeat this process. But for my trying it out a few times, and it doesn't look like you need to repeat it maybe once more. Maybe not even. The results I will show you here, I did not make any representation. I didn't calculate. So it looks like it will more or less be the same regardless. So moving on, I've tested this then on the Danish energy system 2015. So all the numbers here is from 2015. This here is the Nord Pool spot systems price in 2015. So that will be the one we use as external electricity market price. We will ignore the fact that we also have connection to Germany. Because we have investigated and actually the prices is mostly correlated to this. That's some of the things that Søren is looking into. And now Lars is left. So if you have any questions, please send me. Then we put it into an energy plan model for Denmark. And then here, this is just to show that it's quite the same system. This is the statistics from 2015. And then this is the simulated model I have in energy plan. And this here is the total primary energy consumption in Denmark. So they're quite similar. There's a few differences, and that's mostly related to the biomass CEPR band that gets subsidy. I cannot really simulate that in energy plan. It gives a bit of a skirt to the small scale. But overall, it's more or less the same system. An operation. Then after I put it into the model, so take the electricity price. Here, this one, put it in that model, and then I get this imported. Then afterwards, I take this and then I try to say, well, if I can subtract this from it, what would the difference be? So this here, the blue one, again, is the actual price, and the gray one, that is when I subtract the Denmark system from my Nord Pool. So you can say that is if I took Nord Pool and then kept that here, and then took Denmark and then cramped it out, what would happen then? Had happened in 2015. Then I take this gray price, put it in again, and then I get then I have a new electricity price, the one I want to check up on. The green one here. And the blue one you can see behind, that is the actual price. So you can see it follows quite neatly actually. There is some differences around here, for example, you cannot really catch this one, but it actually catches this one quite well. And here also. So there are some differences, and of course there is a lot of things we cannot simulate. I cannot simulate when there's a plan out for out of operation because there's something going on, or when there's a cable out. But it actually catches quite nicely. Actually. Pretty close. So, why this method? Well, let's say I didn't want to simulate 2015. Now I've already done that. It's boring. I know that issue. But maybe I want to investigate something like this. What happens when we start to install more variable renewable electricity production? So we have onshore, offshore, and PV. That is the three ones we normally operate in Denmark. And then I took this here is 2015 capacities, and then I went to 2000. The EDA plant looked into that. What is the capacity in 2035, and what is the same in 2050? And then you can see you get this quite steep capacity increase. So when we see this capacity increase, we would expect that we have an effect on the electricity price, and we would like to see whether or not it actually has an effect on the missing money and the variable, and we want to quantify it. Because it might not be an issue that this occurs if the price of these production units goes down significantly, or we do something else in the system. So this is then what I get when I take these capacities and put into energy plan, my model from 2015. So this is just if I only just increase the amount of electricity in the system from variable and do nothing else. So this here is the 2015 average, and you can see it decreases quite rapidly. And the reason why it then has this curve is because of the transmission time. At some point we cannot transmit anymore, and we will not affect the system price anymore. So that is one thing you can say, but again, that might be a bit boring because, as I said at the beginning, we already know this. We want to quantify. or we want to see what other things could happen. Let's say I wanted to investigate, should I go for heat pumps to help with the merit order problem and the missing money problem, or should I go with electric vehicles? Maybe that's my question. So here I took the capacities and the demands we have in either 2050, and then I plot them in. So the blue one, that is the graph we performed. 2015, if you do nothing else, you just install a lot of renewables. And then the green one, that is if we put heat pumps in the district heating. And you can see that actually increases price. System price quite a lot. And then actually also, at some point, these start to converge, become more or less equal. But the green one stays on top all the time. Meaning it looks like that the heat pumps in the district heating actually is better for keeping the electricity price off, at least in average. And you can also there's not that much of a difference actually between these two types of electric vehicles installed. There is a bit more difference down here. There's no difference up here more or less. But there's a bit more difference here where the smart charge actually starts to have an effect. So one thing, of course, looking into the average system price, but I said I want to investigate the merit order and the missing money. So the merit order. This is the merit order for million euros earnings on the spot market of electricity sale per gigawatt of electricity capacity wind power and PV are installed. And I've not made a distinction between PV and wind. I just put on one pile. So if I don't put in new demands in, this is what will happen. It will start to lose the income quite rapidly. As I say, this is very new information. I made the last calculation yesterday. I want to change some of it today, but there was an issue. So take it that this is practice. Take what it is. But of course, ask any questions you have to at least attempt to. And you can see the same effect as before. That heat pumps seem to be one that actually increases the most here. But there's a bit different when you then look into the missing money issue. And that is where it actually is very important that we have to make a model to simulate this. The reason why I'm saying that is here we don't see a different story. We saw an effect, a very positive effect from heat pumps on the merit order effect, the income from the wind power and the PV. But we actually do not see the same level of effect on thermal plants, meaning the power plants and combined with the power plants. The green one have here, you can see it does increase the total income of the thermal plants a bit in the beginning, and then also makes it a bit more heavy going forward. But actually what helps with these plants the most, it seems, is this one. And of course the reason why this one is heat pumps does not is because we also take away the heat demand from the combined heat and power, meaning we'll have to operate more on power plants that's simply less efficient and more expensive to use plants. So here then you can see the strength of making this more complex simulation calculations. But again, this is graphed. Please take it for what it is. That was my speedy version of this. Any questions for Susanna? Oh, mine also.
So right now you're looking at either heat pumps or EVs. Mm-hmm. Do you also look at the combination of both? Or?
Yeah, I've considered that at least, but at some point you always have to ask the question how much more to look into. For me, the most important thing I will look into here is probably this. This, what should we do first? I mean, is there a process where it makes sense to start with the heat pumps before we start going into EVs or the smart charging needs? I've also considered looking into vehicle to grid to see how much that affects them also. And electrolyzers especially. And I've not really found a good way of doing that yet, though, but I want to investigate more than this. This is just preliminary.
Yeah.
See this word comment. I'm not sure if it's actually, but previously we said something like that in the beginning the heat pump can do a lot of good.
Yeah.
but then at a certain point, they cannot do very much good in the longer. But at that point, you need the transport somehow to come. That would be
That's basically what it's talking about. Right. I mean, you can see the effect here. The heat comes first, yeah. Then at some point it starts to converge. And actually it becomes, and of course if I then added this one, these two, I think the price will be higher because it's just added demand. Yeah, I have to fulfill.
Yeah, but then you have to a little bit different, but then you should have a heat pump alone.
It is
at a certain point.
Oh,
And then they add the other top.
Yes,
And then
yes.
see how the weather and some of one.
Yeah.
But that could be interesting to see that.
But it does have a positive effect on the merit order. But the thermal plants, it's a bit more of a blurry picture.
Yeah.
For the missing money, and that is actually a bit interesting from what we also work with the iron.
So the voice heat pumps are constant, right?
At least it doesn't really help in the beginning, but it actually keeps the income up.
The increases in electricity supply, but still the heat pump.
Yes.
Would you see the same effect when you implement the 50% heat savings Paul talked about?
That's a good question. That's actually one thing I want to put in this. So, yeah, it's something I think that would be interesting to look into because that might actually make a huge difference in this part.
This is something that the Jacob once analyzed years ago. How this heat savings, how they influence one another and this sort of balance.
Yeah.
And that's really good.
It's very connected. But I mean, here I don't talk about. I mean, Jacob he looks a lot into system costs, and this here doesn't really consider system costs. I mean, I cannot say one scenario is cheap, and what I can say is where does the money flow. So, what is the effect on each individual needs? More questions?
Yeah, just to understand, so your model also shows that the merit order effect and the missing money issue cannot be solved only by heat pump.
Yes.
Eventually
Yeah.
it will
Yes.
be a big problem.
And I'm not even certain if I put in everything we have needed, for example, that it would actually solve it. The issue is that the main component for the flexible consumption is not in this graph yet, and that is the electrolyzers. There are around 9 gigawatt of the electrolyzers in the electricity side, meaning that is a huge consumption. It's around 40% of the total demand of electricity. So that's of course also why we that's installed up to this level here. But I'm not sure we will actually see it, but I think the price will still decrease. But I want to investigate, so that's also part of it. Good question.
And then of course, interesting to compare to the diagram I showed 2 weeks ago where the code have invested a lot of heat pumps, but the transmission lines versus the electrolyzers.
Yeah, and some batteries.
And the batteries.
More questions?
Oh.
Yeah, okay. Then we will stop.